Welcome to the carbon capture solution presentation, and I'd just like to give my thanks to Christopher, Jalen, and Keaton for putting in a lot of work and making this project possible. So let's get going. Our problem definition. Well, over the last 100 years, we've seen a drastic rise in the levels of concentration of carbon dioxide in our atmosphere. That's the graph to the right. And this kind of what's happening here is we're getting about 5 atomic bombs worth of heat energy being released into the oceans every single second. And due to this that's due to this massive amount of carbon being released. And this resulted in the 10 warmest years in the past century, all occurring since 1980. And this causes icebergs to melt, which causes ocean levels to rise. And essentially, we're on a trajectory for mass extinction and destruction if we cannot solve the global warming issue due to carbon dioxide pollution. So let's continue on. Who cares about this problem we're facing? Well, all industries should care, and I'll give you some reasons why here. So, with the oceans rising in acidity, that's causing fishermen to struggle. And the reason that it's rising in acidity, when you combine carbon dioxide with water, you get carbonic acid. And carbonic acid eats away the shells of sea creatures that fishermen use to fish and sell and eat. So, this is really bad for their business. Also, ocean life is the largest source of oxygen on the planet with all of its fauna and flora. And that is not good news for humanity if the ocean is becoming acidic, which is killing those organisms who were making us oxygen, and now they're not. In East Africa, we have a pest problem due to carbon dioxide. Locust numbers are rivaling a biblical plague level, and this is affecting farmers in that region. So those are two examples of industries that should care. Also, the individual, and here's another example to support that. The wildfires that plague California every year, 52,000 in 2020 alone, are due to an increase in carbon dioxide in the atmosphere. Global warming causing drought, therefore, fires are easier to start. Now, let's go to the next slide here. Evidence of the problem. Starting June 1988, world temperature has risen 0.32 degrees per year. Ice caps are melting. Ocean levels are rising 2.46 millimeters a year, and they are absorbing about 7.2 to 10.8 billion metric tons of CO2 in oceans a year. And here's the sources where my team got that information. So let's look at a solution to the problem and kind of lighten the mood a little bit. So here's my team's main idea. If you look with me to over to the right to this figure, you're going to see a four-stage process. So in stage A or one, we have a fan unit that's going to suck in CO2 rich air, right? That air is going to be sent through a carbonic acid producer to a reaction chamber and eventually to a potassium carbonate production room. Now, let's talk about that a little more in depth, right? So the CO2 can be dissolved from air into water, and that's going to create our carbonic acid. Our carbonic acid is a liquid solution, which can be funneled through this pipeline to this reaction chamber, and that's gonna produce our potassium carbonate. And right here is where we're going to add in potassium hydroxide with it, which is a reactant that we're going to need in the equation. So to explain that further, let's continue on to the next slide. So here I've drawn out kind of a typical, this represents one of those long rows you saw on the last slide, right? Represents this whole thing right here. So here we have our fan taking in air, and here's this tube that represents the rest of the processes that are going to happen. So another question that this solution needs to answer is how is the plant going to be powered? Because we don't want to power the plant with just more carbon, right? Burning more carbon because, well, that's not going to solve our problem, is it? If we're capturing CO2 but releasing it in order to capture it, this doesn't make any sense. So to solve this, our team decided to power the solution with solar arrays that are going to be on the top of the building. So here you've seen that I've drawn one out right here. In the picture on the right, it's next to the row, but it would be above it on the roof of the building in reality. So let's continue on to what is going to happen on a chemical level. So once the carbon is in carbonic acid, which this is the equation for that process, right? H2O plus CO2, we're going to get this carbonic acid reactant right here. Okay. So once you have this carbonic acid reactant, and let's pause and look at carbonic acid's molecular makeup for a second. We got a hydrogen bonded to an oxygen, to a carbon, to an oxygen, to a hydrogen, and that carbon is also bonded to another oxygen. Now keep in mind, all the carbon's valence electrons have been filled, and we have 2 lone pairs of electrons on each oxygen atom. Now, this is important because carbonic acid can thus react since we have valence electrons. So we're going to react the carbonic acid with potassium hydroxide in that reaction chamber I showed you. And when we add in the potassium hydroxide, a chemical reaction is going to occur, which will produce H2O and K2CO3, which is potassium carbonate. Now, that's important that we produce this water as a result, because if you look back up to equation 1, water is one of the reactants we need up here. That makes our solution more efficient because it's cyclical. Now, let's continue on to the next slide to get an overview of the solution. Basically, here's the holistic view, right? So I showed you that each row is going to perform all of those reactions, and it's going to trap the carbon, leaving us with our product, potassium carbonate. But how are those going to be housed? Well, there's going to be a number of those. If you look at the complete view, a number of rows inside of each plant. And the plants are going to be in the shape of a dome. Not really a dome, but more of a section of a cylinder. On top, we're going to have our solar arrays that's going to power our plant. And here you see the fan units. That's more obvious on the frontal view. So why do we want to produce potassium carbonate? Well, potassium carbonate can be used to produce glass. It can be used as fertilizer. It can be used in pharmaceuticals. And more importantly, it is a solid. Can be a solid. And so we've trapped the carbon. We've taken it out of the air. So let's continue on. Here's some other solutions. Google, HP, Tesla, Microsoft, and Apple are all trying to help as well. Tesla's electric cars have eliminated 4 million tons of CO2 from ever entering the atmosphere. Google plans to be carbon-free by 2030. Some companies are trapping carbon in fluid to store it in the ground. Right? It's similar to our solution, except we're going a step further and making a product out of that fluid. A company called Blue Planet is transforming carbon emissions into carbonate rock for concrete. And this is a pretty interesting idea as well. So what are the benefits of our solution specifically? Well, we use a direct air capture method, which allows for a resource to be produced. And this also captures more CO2 than agricultural carbon farming. Now, you may also hear about a solution called reforestation. The problem with this is that if we want to use the product that makes, which is wood, we have to chop the trees down, and thus stopping the means of capturing more carbon. So it nips itself, and that doesn't really end well, right? So our solution produces water as well, which is a reactant in the first chemical process, and thus it's cyclical, as we already described. This means our solution is efficient, and our product can be used for many things. So I would just like to thank everyone for watching the recording. That's our solution to the problem. Thank you.